virtualization, and cloud computing. He is passionate about open source software development and contribution. He holds an MS degree in computer science and has 3 patents. Welcome, sir. I am sure each one of us will benefit from this lecture. Over to you, sir.
Okay, thank you for the kind introduction, and good morning to all the faculties and students. Um, so I'll be presenting about the low-level programming on single and multi-core architectures. I'm going to share my screen, and we'll start off with that. Okay, so I've started sharing. When you are able to see on the screen, please let me know.
Yes, sir. We're able to see this.
Okay, so let me try to make it full screen. All right. All right, so it's full screen. I cannot see you, but I hope you can see me and the slides.
Yes, sir.
Okay, now, so we have a 1 hour session today. Obviously, we cannot talk everything about it, all the concepts in detail. So I'm going to talk about these three things primarily: the instruction set architecture, assembly language programming, and some of the challenges we face when we go for multiprocessor and multi-core systems. Right, so I have a few slides on each of these three topics. My goal here is to not explain everything in detail, but to provide the right level of next level details on each of these topics beyond what you have learned so far, so that you can go and explore by yourself. I also want to induce some kind of curiosity for some of you who are interested in this area, like operating systems, device drivers, kernel development, embedded systems, or real-time operating systems, hypervisors, or robotics controllers, right? So if you're interested in these areas, some of the topics that I talk today will be of interest. And what I would like those who are interested to explore this more. There are so many challenges to be solved, and if you need some more details or links or references, I'll be happy to help. So let's start with instruction set architecture. Now, ISA is something I believe you have covered to some extent in your computer classes. So I'm not going to really go into the definition part of it, except that I'll just say it's an abstract model of the computer. And what do we call as ISA? The typically we see the registers, the instruction set, the addressing modes, memory architecture, interrupts and exceptions, and the output, right? So when we put all this together, we typically say that is ISA. Now, why do we need this? So if you really look into computer science, it's actually full of abstractions. What we say as process is an abstraction. What we say as file is another abstraction, right? So we have this middleware, software, firmware, and the biggest abstraction in computer science is ISA, because it divides the hardware and software. It sits right in middle of both. Both are big domains, and ISA is what binds both of them together. So long before ISA, it used to be microcontrollers and tiny embedded programs, and they used to write this or develop these programs which are very specific to each microprocessor. And when somebody designs a new microprocessor, they will rewrite their logic using the new architecture and instructions for that particular processor. But over time, that was found to be very, very complex and unnecessary. So with this ISA, what it promises is binary compatibility. That means you write the software, you compile it, create a binary code, and it's guaranteed that it will run across multiple processors, even new ones, without any modification required. Right. So uh, what I can say is that the code that was written maybe 30 years ago for very old processors like the Intel 286 or 386, they are still they can be still executed on the modern latest Core i7 processor because Intel maintains this compatibility over such a long period of time. And this created these two huge fields of hardware and software engineering. Now, the second point is ISA allows for innovations and independence. So the hardware engineers and the hardware companies can go independently and innovate on their fields. They can create new microarchitectures, new fabrication process. They can increase the clock speed or add multiple cores, add many accelerators, new instructions, and keep on optimizing this. Software engineers don't have to worry about it. They can still follow the same ISA and write their software code, and it would run, and it may run even better on the new hardware. Similarly, software engineers, typically the OS developers and device drivers developers and RTOS engineers, they do not really have to worry about what is the instruction pipeline, what is the clock speed, or what is the internal architecture of hardware. As long as they are compatible with ISA, they can innovate in their fields. So this actually accelerated the innovation greatly. And there are different ISA instruction set architectures, and the dominant ones are x86, which Intel, which I come from, the company I belong to, follows, and ARM. And there are other minor architectures which you may have heard of. So talking about the x86 ISA, this was developed by Intel sometime in the year 1972, I believe, when this 8086 processor was introduced. So at that point, I think it had some 175 instructions, and it was very simple. It was 16-bit ISA. But if you take the latest Core i7 processors, I think there are more than 1,500 instructions, and it is 64-bit. So what does 64-bit mean? So that is the size of the data which these instructions can operate. So this ISA is actually continuously been improved for the last 30 or more years, and I believe it will continue to evolve. And most of the desktop servers, they're all predominantly x86. Currently, Intel and AMD are the key developers of processors using this ISA. And talking about Intel specifically, we have multiple processors like Atom. You would have heard of Atom processor, Core, i3, i5, i7, and Xeon. So all these things, all these processors follow the same ISA, and the code that we develop for one processor is compatible across all this. Now, finally, I have to tell about this one point. There is something called this Intel Software Developers Manual. It's a PDF file. You can just Google it. It's available at Intel website for free. It is actually a very big manual. It's about more than 5,000 pages big or thick, let's say, and it explains all the everything about ISA and something more, all the instructions, some of the abstractions, how to optimize the system, how to write the startup code. It gives a lot of information about the x86 ISA. So those who are into this area, maybe it's a good idea to download it and refer to the appropriate sections. Um, so one interesting point from my side. So when we were doing our undergraduate bachelor's degree um, maybe 20 years ago, my bachelor's project was developing an assembler for Intel processors. So I developed a simple assembler which can convert assembly language code into binary code. So at that time, I remember the SDM was little smaller. I used to take printouts, and this used to be um, not 5,000 pages, maybe 1,000 or few thousand. So now these are available for order as well. But anyway, PDF is available for free. Who are interested can download it and make use of it. So let's talk about ISA in detail. So assume that you're a programmer, not a C or Java or Python programmer. Let's say you're a systems programmer writing code in low-level language, assembly language, let's say, and you are developing RTOS or firmware for a microcontroller, which is, let's say, x86 based. What you have in your hand is actually what you see from ISA point of view is only the registers, and you have instructions, right? So what does a processor do? So you write your code, you convert into opcode, you place it on memory, and then the processor can scan through the code, take it one by one, and execute it, right? So that's all a processor does. There's no other way to control it. So from a programmer's point of view, this is all you see. We see so many registers, various types of registers, control and data and bounds and XMM, OMM. These are all very wide registers, 128, 256 bit. They are used for accelerating various operations like image processing, cryptography, or video processing, even machine learning. And you see the address space, like 0 to whatever address, like in this case, it's 64-bit. So it's that range of address is what you see. Now, there are many types of registers. What you learn is typically about this EAX, EBX, ECX, and so on, these general purpose registers. But if you go to system level programming, you'll need to know about various things like control registers, status registers, interrupt mask registers, or MSRs, model specific registers. Each CPU may have its own special set of registers, which you should know about. And there are MTRRs, memory type range registers, which say which region is writable, which is not, and so on. And there are so many internal registers which are not really exposed in the ISA, but available for debugging. So you have all these registers. Now, when you write an assembly language program, you really worry about which register should I use? Because when you write a C program, for example, you have an abstraction called a variable. You declare a variable integer I or X. You don't really care about which register it actually is used for that, right? The compiler takes care of it. But when you write a real assembly language program, you have to allocate registers for each variable. Now, register allocation is actually a very complex problem. You can declare maybe 10 or 15 or 20 or 100 variables in a program, but in fact you may have only, I don't know, 16 registers in your CPU. So the compiler actually it goes through this register allocation algorithm, and it will reuse the registers, right? So if you learn in deep about the compiler design, there are many algorithms like graph coloring problem, which they use for identifying the right registers for each of the variable. Okay, let's quickly go through a microarchitecture. So I just explained that the ISA is that particular layer which separates the software and hardware. So hardware can independently improve themselves. So if you see the trend of CPUs, maybe 5 years ago, you get a CPU and you run a program, it may run at some speed. But now the same program with a new CPU will run much faster. Why is it faster? is the CPU speed increasing so much? Not really. In fact, the CPU speed can even reduce. Let's say 5 years ago, you had a processor which had 3.7 gigahertz speed, but now you have a processor with only maybe 2.1 gigahertz, but still the program will run faster. So that's because beneath the ISA, there are what you see on the right hand picture, right? So the way of implementing an ISA is actually the microarchitecture. So you might have seen a picture like we have CPU, we have cache, and we have memory, and very high level logical diagram. But that's not how actually it's implemented. Actually, if you see each block, if you zoom into it, it's a very complex piece of hardware. There are so many components involved. Even this picture is not very detailed. Um, and this implementation can change every generation, every 2 years. What you see here, it may change, but still that will retain the same ISA. So the code compatibility is maintained. So this is the crux where optimizations are made, which makes the program run faster. So I'll also talk about this TikTok model. Um, so there are two things to understand. One is this microarchitecture, which defines this what is shown in this picture. What's a decoder, what's a branch predictor, and all this instruction decoding, scheduling, execution engines, right? So this is the microarchitecture, and then we also have the fabrication process, like which gate to use. Is a MOSFET or it's a FinFET, or which etching or which lithography procedure to use. So that's entirely different field. So these two fields, they improve independently. So TikTok model is something which Intel adopted, where in 1 year they will take a new microarchitecture which has so many improvements, but retain the previous fabrication process. In the next year, they will retain the same microarchitecture but take the new fabrication process. So with this approach, we don't change both of them together. If we change both together in the same year, it may create some um, defects which will be difficult to identify where the problem is. So we'll have this kind of TikTok model where we go in steps, and there are huge teams who improve the microarchitecture independently, and there are other material science engineers and chemical engineers, physics engineers who look at the new silicon or germanium or the new materials for this microprocessor, and also the new MOSFETs or FinFET, or what's the next innovation, right? So these two teams work independently. So yeah, so I'm not explaining the whole picture here, but the point which I want to show is that explain about this concept of microarchitecture, which is the actual implementation of the components in a CPU to provide the ISA on top of it. Now we'll talk about registers. So the registers are one of the key components of ISA. So if you have done microprocessor programming, you would have written some instructions like move, EAX, EBX, and they're all operating on registers. So registers are very one of the fastest data storage locations. They are a temporary storage locations, obviously, and they're all directly addressable by instructions, and there is no delay in accessing the data in a register. Um, so every new generation of CPU, they add new registers or make the register size bigger, so that we can put more and more data on the registers, and in that approach the execution will be faster because fetching from memory is very slow. um, let's say I'll show this picture on the right side. So this shows the memory hierarchy, which is something very important to understand. So this shows all the places where data can be stored. Starting on the right on the top is what we have, the registers. These are very close to the CPU execution cores, and they are also usually made of the same transistor or gate material as the CPU core. So when an instruction wants to access a data from a register, it's extremely fast. It's pretty much in the same clock. There is no delay. Now there are multiple layers. Below that, we have all the cache layers, L1, L2, L3, L4 cache. So these are again temporary data storage locations. And as you go down, the size, the capacity increases, but the access speed reduces. So if, let's say, if data is not there in register, it will try to access from memory. But before going to memory all the way down, it will check in the cache in that order. If it is in the L1 cache, it's very good. It will pick up from there. There's only a small increase in the time. If not, in the L2, L3, and so on. By the time it misses everything and goes to main memory, it's like orders of magnitude slower. And if it's not in the memory, and if you have to load it from the hard disk, for example, and again, if you see the disk drive, that is the slowest. So, so the point here is that to really optimize the program, we need to have the data higher up in that order, but the capacity is limited. So all the way from registers to cache, it's all not visible to programmers. They're all managed by the hardware. So hardware has a lot of algorithms built in to manage all these caches and registers efficiently. Let's say you have an instruction which tries to access some data, like move some data to a register, and the data is not there in the cache. It has to fetch from memory, right? CPU instruction executes nanoseconds, but here, if you go all the way to memory and come back, you have a delay of 63 nanoseconds. So for all that time, it will wait. In fact, CPU could have executed some hundreds of instructions at that time, but because it's not available in this cache, it has to wait. So it will slow down the program drastically. So we have this prefetch approach where instead of waiting, the CPU will automatically prefetch the data, which I will cover maybe in the next few slides. So when I talk about registers, this is what I just want to provide an insight to. Now, we'll talk about instructions. These are the key part of the ISA again. These are like instructions are like control, um, how we can control the execution of the processor. Uh, we can write the instruction in the mnemonic form, which is like move or in, out, etc. But they're all converted into opcodes by the assembler. And that's what you have to place in the memory for execution. If you talk about ISA, x86 ISA, the instruction length can be variable. So again, if you refer back to the SDM, which I was talking about, we have a very simple instruction, for example, uh, in instruction. It takes data from a port and moves to a register. But we have very complex instruction, for example, packed multiply or AVX, advanced vector instructions, where it can take a huge array of numbers and do an operation in one go, in one instruction. So because of the variety of instructions, they're of variable length. Variable length here I mean, let's say if in instruction is transferred into like 2 bytes or 3 bytes, an AVX instruction can be much bigger, like 16 bytes and so on. So that's what the complex instruction set is all about. We have many instructions like 1500 or more, and doing very complicated mathematical operations in one instruction compared to RISC, which are consisting of a smaller set of instruction, and they don't do such a complex operation for every instruction. And there are advantages and disadvantages to both of it. Now I'll talk about this, how the instructions are executed. Um, Long ago, it used to be scalar operations. That means CPU will fetch one instruction from the memory, decode it, execute it, and then go to the next one. Now the problem is that if one instruction is waiting for a data from memory or a input from user, for example, it is blocked. The next instruction cannot be executed. So that's why CPU designers have this concept of pipeline architecture, where each instruction is going through this various operations in parallel, which they call as instruction level parallelism, which actually gives forth to the superscalar architecture. So the CPU has multiple execution pipelines, and each instruction that we see, for example, move, which I'll explain more in detail, is not something which CPU can easily understand. The move is actually very complex instruction. So it is decoded into multiple micro ops, and micro ops is what the CPU hardware actually understands. So when you break down any instruction into multiple micro ops, micro ops can be like fetch and then do some operation and then move back to memory, right? So let's say we have some red and blue dots. These belong to different instructions. They're all the micro ops corresponding to a particular instruction, and they are all executed in parallel at various stages through this pipeline. In this picture, we show a four-stage pipeline, and some newer CPUs have even bigger pipelines, like 7 or 8 stage pipelines, and they can do multiple parallel operations. And CPUs have many pipelines like this, 7 or 8 queues. So much instructions are in flight and execution at the same time. So here it shows the four-stage instruction pipeline. The first step is fetch. That means you have to fetch from memory or even the hard drive. It may be a binary file in the hard disk, so it has to be fetched, and then it has to be decoded. Decoded means you convert the opcode into set of micro ops, and then you push to the execution engines to execute each of these micro ops. And once it is all done, we collect the results and write back to the memory. So that's the process of executing one instruction. Now I'll talk about the second part. Now I talked about the microarchitecture, and now I talk about the process innovation. That means the actual silicon or hardware, how it is improved, right? Is a just one slide quickly goes through. Um, so we know that CPU internally has all these transistors and gates and FETs and so on. So even that goes through multiple levels of innovation. So as you know about this Moore's law, which says that every 2 years, the the transistor density doubles, right? Let's say if you have 1 billion transistors in a CPU now, after 2 years, it will be 2 billion. But then the CPU size will be the same. So that means we have to reduce the size of each transistor or gate by half, or roughly around that. So that's what this 1410 nanometer evolution says. So this individual transistor gates are reduced in size. They go into smaller and smaller nodes, and it's not that easy. For each of this generation, we have to find some new techniques. For example, in Intel 10 nanometer, they use something called super FinFETs, and the fabrication technology. Everything has to, follow this approach. So this happens independently. They don't have to really worry about, because they all still maintain the ISA. So at the bottom, we have this fabrication technology, then we have microarchitecture, then we have ISA, and software will be on top of this ISA. So that's how the whole picture looks like. Now, another picture which I usually show in any kind of this assembly or low-level programming kind of discussion is this memory map. So when we think about memory and when we write a program, we think that the processor memory is starting from address 0 all the way to, let's say, 2 power 64 minus 1, right? So that 4 gigabyte or 4 terabyte kind of range, it's all available. But in reality, the addressable space in memory is not contiguous, and there are like n number of partitions in them. So this depends on each architecture. Here I'm showing an x86 typical modern memory map. And if you're a embedded programmer or RTOS engineer, or device driver, for example, right? So this is something which we have to really look at, um, because we can't just use any memory location randomly. They're all predefined for certain use. So from the right hand side, if you see less than 4 gigabytes, right? So this is a 32-bit system, and beyond that, there are many um, regions which are specially allocated for graphics, for example, here, and there are PCI memory mapped regions over here on the top, for example, and main memory, which is the DRAM, is mapped somewhere here. There are flash, epic spaces, interrupt controller access, MSI interrupts. So all these things are mapped in specific regions. These are all predefined by the architecture, and looking at this spec is very important if you're developing an OS or a RTOS. So on the left hand side, we see this 1 megabyte DOS region. So long time back, when DOS was the primary OS, we had a 20-bit data or addressing range, and that will enable us to access 1 megabyte. And within 1 megabyte, we have this kind of partitions. Now, the interesting thing is that this is still maintained. So theoretically, DOS can still run on even the latest processors because these memory partitions are still maintained. And whatever memory we have in your laptop or desktop, like say 4 GB or 32 GB, they're all mapped in this kind of OS visible DRAM region. I'll talk about the PCI MMIO, for example, memory mapped IO. So they use very specific defined regions here. Um, yeah, I don't want to go details, but just remember that the memory is not a simple blank area. It has very, very specific divisions there, and we are allowed to do only specific things on each of these regions. Now, let's quickly talk about IO, which is again a key part of this ISA. Um, so you would have learned about port IO and memory IO, right? Memory mapped. So in the olden days, these two used to be like equal. Some devices go port mapped, some devices go memory mapped. But nowadays, port mapped is extremely rare. For very, very slow access, for very legacy devices, we use this port map. Now everything is memory mapped because memory mapped is way faster. It uses the CPU address bus, not a separate IO line. So IO mapped, so use this typical in-out instructions. Again, only for legacy or very, very slow speed access. Everything else moved to memory mapped now. And I'll just quickly talk about PCI. I don't know if you have this topic in the course, but PCI is the peripheral component interconnect, right? So this is the interfacing technology. How does a CPU talk to all the any IO devices? So PCA forms the backbone of x86 architecture. That's the core bus which all the other devices are attached to. So CPU either talks to the DRAM or to the PCI bridge, host bridge, and everything else is from that point. I just want to give a flavor of this. I'm not going to detail about this because of I'm running out of time probably. So I'll go a little quickly. Now let's jump into the assembly language, right? So I hope you all know about assembly language. Anyway, just starting with a quick introduction. On the left-hand side, we see C program, which is a high level. Obviously, not the very high level. There are much higher high-level program languages now, like Python or Go or Rust and so on. But C is still high level. So we have this maybe three-line program on the left side, C program, just the famous Hello World example. All it does is just print this string. And if you are using Linux, you have this compiler called GCC where you can use that to build the program or compile it. But now I'm using this special switch called -S. Maybe you're aware of it. So what it does is actually converts this C code into assembly code, which I shown on the right side. Now I'm just showing this just for a comparison. In the C, just 3 lines. We're just calling one function, which is print. Let's go through this assembly language program real quickly, right? So in the initial phase, we are defining a string, hello world, using the dot string primitive. And then the main function starts. It starts with a few instructions like push q, move q, and sub and move L, right? So these 4 or 5 instructions are for setting up the stack segment, creating a new stack for the main program, readjusting the stack pointers and base pointers and so on. So typically, if you disassemble any program, you find this kind of frame initialization instructions, and then you have this move L, right? So you see move L, move Q, and so on. Q is a subscript which stands for quad. Quad is the double word, 64 bits, and L is for the word. So here we are moving the string into this register and then calling put s. So this is again a glibc function, and right. And finally we move 0 to ax. This corresponds to this return 0 instruction, or the statement. So this is another convention, right? For any function that we write in assembly, we put the return code into ax register and then leave and return. So that's what is returned to the caller function as the return value. So this expands to this many lines, and this is not the full assembly, right? So if you use this obj dump command on the compiled program, you will find even a bigger program because it will expand this putters and other calls. It will be even bigger. I just want to show how it maps to how you the high level program that you write maps into a assembly language. Now, why is this important? When you are developing programs in the area which I was talking about, the operating system or embedded or real time, you will constantly have to get into assembly because, for example, if you want to manipulate some register, which is like control register, or you want to execute some instruction like pause, there is no C equivalent, there is no C function call to do that. So you have to directly write that in assembly. And sometimes you see some stack trace or code dumps, and you have to go to the assembly level to really see what's going on, right? So just a comparison of this assembly versus high level, right? Assembly is always machine dependent. We have to really know the ISA to write anything. High level, you don't really worry about it. It's actually quite complex. You can see from this quick discussion, and it's obviously non-portable. You can't take this and this maybe is a 64-bit assembly code. It won't work on 32-bit or 16-bit or across other architectures, but C code will obviously work. We can have to build for it. And it's always difficult to debug. Now, quick discussion on where exactly assembly is used. So this is something which I always tell. So the early part of any OS is always assembly. So this example on the right shows that we use some instructions like CLI, CLD, right, or LGDT, LIDT, load GT, interrupt, descriptor table. All these things are very, very machine specific, and there is no high level equivalent for this, right? And also when we execute the early code, there is no stack, and assembly can work without any stack, right? So that's the advantage we have, and we can pretty much issue any instruction which the ISA supports, which high level you can't do. So, but then writing assembly is like you'll be writing tons and tons of it, which can be easily simplified using high level, right? So only those critical things like early startup code or scheduling code, processor state changing code, um, system level calls, right? Those critical sections where there you can't write with high level, that's where people use this assembly language. So this code shows what are the sequence typically every processor goes through before going to high level. So I think this is hiding me, but let me move it away. Okay, so finally you see jump main right at the bottom. That's where the C code starts. Before that, there are sequence of steps which it goes through. I'm not really going through the detail because I'll be running out of time. Okay, so other parts, other places where assembly used is to optimize the code. I mean, you can write very optimized code in C program, but that's no match for assembly language optimization. So I'm giving an example of this memcopy from Linux kernel. You can see this file over here. This you can open it and check in Linux kernel source code. So I'm showing two versions of this memcopy function. Memcopy, you'll all be knowing that, right? You'll take a buffer from one location and copies to another place. So it can be implemented in assembly as like this, or shown on this left hand side. So we use this instruction called rep move sq. So it will repeatedly move word level as once you load the counter and destination points on these registers. This rep move sq will take care of it. Now, let's say if I ask you to write a memcopy function, you'll write for I equal to one, sorry, 0 to that length. You assign that to the new pointer, right? So that's like byte level copy. Now, the more optimized one is word level copy. That means you copy 4 bytes at a time. That's what this function does. Is doing a move sq. It's like word level, and then whatever is the reminder. Let's say we have 18 bytes of data to copy. You copy 4 by 4 4, and then after 16 you'll have 2 bytes left. So those reminder is copied by move sb instruction. So here there is no loop, but still we accomplish that by rep, which is actually very, very fast. But then that's not enough. So that's even enhanced faster string copy in the kernel in the same file. So here I'm not showing the full function. It's like hundreds of lines of code. Here they are using very, very detailed knowledge of the CPU, like the cache hierarchy and how this instructions, which registers are the most optimal, and even more advanced memcopy algorithm to achieve even faster speeds, right? So this will actually speed up the kernel really, really. Uh, it will optimize the kernel so much, which cannot be done in high-level programming. So now, this again, I'll talk about it quickly. So when we talk about assembly language, we have all these instructions like move, int, IO, in, out, pause, monitor, etc. Are these instructions directly understandable by the hardware? Actually, it's no. So each instruction is actually divided into multiple micro ops, right, which I was talking about. And here I'm showing one very simple looking instruction, move, between two registers, but actually it expands into this huge algorithm. It may be surprising to you. This snippet I took from the SDM document, where each instruction is explained in detail, and they also explain what happens when you execute this. Because executing, like copying from one location, one register to another is not that easy. Because if you do a copy from memory to another register, we have to check so many things. For example, if user is executing this instruction, he cannot move some data from a restricted area, right? So we have to check that. We have this processor rings of privileges. So we have to check that. That's the RPL and DPL, right? Requested privilege level and the current privilege level and so on. So there are so many ifs and so many checks we have to do before we actually do the move operation. So when you're example executing a virtual machine and you're running this instruction inside the virtual machine, then again you have to check so many things, whether it's accessing from a different VM or what are the protection levels and so on. So a simple looking instruction is not that simple at all. It's actually expands to several pages of if conditions like this, right? So that's the complexity behind each instruction. Now, I think I have 15 minutes, so let's go to the final topic, which is the multi-core. So I covered two things now. The first is ISA, which I was talking about the registers and how the instructions work and so on. And secondly, I talked about the assembly language programming itself, how and what are the complexities behind it and where it's used. I did not talk about debugging, but yeah, um, about assembly language. Now I'll talk about this multi-core and shared memory architecture. So, so what is multi-core architecture? So in multi-core architecture is where you have multiple cores or multiple execution engines inside the same CPU package. So this picture shows it's like there are like 4 cores now, numbered from 0 to 3. When you have this multiple cores, there are so many design considerations. Previously, in a single core system, obviously things are simple. There is only one execution engine, and it will still allow us to run multiple processes in parallel. So there, it was only time division multiplexing, right? It gives a illusion of multiple programs running together, but they're all time slicing the same core. But in a true multi-core architecture like this, you can have different code segments executing on each of these cores. And that actually creates so many complexities, right? So what I show as LAPIC is the local EPIC, right? So previously used to have only one interrupt controller, the EPIC, central EPIC. But now for each of these cores, we need to have dedicated local EPICs. And then for each of this, typically we should have some caches. And this L1 cache, what I show here is also consisting of 2 caches, the instruction cache and data cache. So I told that each instruction is broken down into multiple micro ops, right? So let's say we have a instruction which the decoder has decoded into multiple micro ops. Now, what do we do with that? Should we throw it away? No. So the decoded instructions is micro ops is also cached, because next time when the same or similar instruction comes, we can reuse the same thing. We don't have to decode it again, right? So that's the point of this instruction cache and data cache. Obviously, if there is a data which is frequently used, always have it on the first level cache. And if it runs out of space, then we go to the L2. And if that size runs out, we go through L3. So this is all transparently managed by the CPU itself, not actually visible to the programmers. Now, again, there are 3 levels of caches shown here. Now, how do we have it? Should we have a common L1 for everybody, or we have for each core? So in this architecture, we have L1 dedicated for each core. L2 is shared by 2 cores, 2 of the cores, and L3 is shared by everybody. Now, the data that core 1 accesses can be in its own L1 cache, or it could be in the L2 or L3, or it could be in somebody else's L1 cache, right? So that's the big problem of cache coherency, which maybe I'll talk about in the next few slides. And then there should be communication between all the cores. So we call as IPI, inter-processor interrupts, which are special communication techniques, methods, where one code running on one core can interrupt or communicate the code running on the other and synchronize, for example. And so this picture also shows this QPI interface and IMC. IMC is the memory controller, which actually controls all the memory. And then we have QPI, the quick path interconnect, which actually, sorry about that, communicates with the PCI subsystem to connect all the IO devices. So I'll quickly give some idea about how this is, and maybe it will make some of you curious to learn something more about it. Now, booting is one of the problems of multi-core. So we have 4 cores, right? And they're executing. How do we boot an operating system? So typically, if you are aware, the first thing that boots is the BIOS on a system, the basic input output system. It's a firmware which runs first and initializes the hardware. So BIOS, one thing to remember is that it's always single threaded. That means it will run only on the core 0. So we have this, we differentiate at boot time the cores into BSP and AP. BSP stands for Bootstrap Processor and AP is the application processor. Um, Bootstrap Processor is one of the cores which is designated to run through the BIOS and the kernel. And once the kernel initializes, it will make use of the other cores. Till then, it's only one of the core is executing. Now, which core do we start with? That is also not hard coded or not predefined. So when we power on a computer, all the cores will actually come up, and they actually sort of fight for this. Who will become the BSP? There is an arbitration algorithm. Whoever comes first, that will be assigned as the BSP, right? So physically, for like 4 cores on a system, we can't say this is the BSP always. Sometimes this core will win, sometimes this. So that's dynamically assigned. Typically, when the system boots, a multiprocessor system boots, one of them takes control and the others are all put to sleep. It goes through the BIOS, the early initialization and the boot. And only when the SMP aware kernel boots, it will initialize the other APs, AP cores, and start using that. So the SCP and init EP, right? So these are some of the interprocessor interrupts, the startup IPI and init. This was some of the ways which the BSP will communicate with the APs uh, when they can wake up and run some code. Okay, so that's about it. So now with multi-core, I will also introduce this topic very quickly about multi-core programming. So typically, if you write an application, the operating system scheduler will choose which is the right core for you to run. You don't really have a control over that. And a lot of programs are usually single-threaded. So CPU will have a scheduler which will pick the right core for execution. But then when your program wants to do multiple things in parallel, then we can use this thread. Thread is one approach, message passing is another approach. So when you have threads, you actually use the system calls to create different instance of execution. And in that case, the scheduler will try to put the threads in different cores so that you will execute in parallel. And it can change because if that's the concept of task scheduling, right? If one of the CPU is underused, the CPU will try to balance it. That's one approach. The other approach is message passing. So in this case, you run statically the process in each core or across CPUs, but then you communicate using messages. There are OpenMPI kind of libraries available, which will help us to implement this kind of programs. So when you go for this multi-core, it actually complicates the programming so much. We have to worry about locking the critical sections. We have to synchronize across multiple execution threads. There could be deadlocks um, and all these live logs and all sort of this parallel programming complexities, right? So which we have to worry about. Now, kernel can also provide us option to do something called core affinity. We can say I want to run my thread on a particular core, so it will pin that particular thread to a specific core that we want. And interrupt routing also becomes complicated because we have this device interrupts coming in, and the interrupt handler can be in any of the cores, right? So the right interrupt should be routed through that particular core which has the handler. For example, a disk is doing I/O, or your program is doing a I/O to the disk, and the disk is sending a DMA data, for example. The DMA handler is in core 2, but the program is in core 0. Then it actually creates a routing problem there. So the scheduler will try to optimize or bring the interrupt handling closer to where it is required so that it's much more efficient. I think I have a few more slides, which I will cover maybe 5 minutes. Now, cache coherency is a very complex problem. It's not for software programmers, but more for hardware designers. I showed this picture where we have multiple cores and multiple levels of caches, right? So cache, as you know, is a temporary storage where we can have the frequently used data. Now, cache is not simple because cache is limited in size. And let's say if a program has 100 variables and it uses one variable at a time, not reusing it again, then there is no point in cache because every time you have to fetch a new variable. But if there is a loop where we are accessing or modifying the same variable again and again, obviously it belongs to the cache. Now, cache is all good as long as it's single core. But when we go to multiple cores, then it complicates like anything. Because the same program can be running on two cores at the same time. And they may be operating on the same variable, right? So let's say one program is modifying a variable x as shown in this picture, and the other program is reading it. Then we have to, as soon as the other program writes the data, we have to copy the same data to all the other caches so that the reading programs can make use of it. Even more complex is when both are writing. If both are writing, then as soon as one write comes, the other write should be logged so that it gets time to synchronize across the multiple caches. Right. So this cache coherency algorithm is one of the most complex part of this multi-core design. And I mean, this left side, I'm showing this a very simplified algorithm of how this cache coherency works. If somebody requests data, if the data is already there in the cache, then what to do? If it's for reading or writing, so we mark the cache as dirty, for example. If we have a cache on both sides, same data, and the other processor has modified it, this will be marked as dirty because it is outdated. It has to be synchronized, right? So for this, Intel processors has this messy protocol, which maybe you can go read through it. Modified, exclusive, shared, and invalid. This like a state diagram which shows all the states the cache can go through to ensure that it's coherent across multiple execution units. And this process is called cache snooping. So whenever a data is CPU tries to access a particular data, there's a snoop signal going through the snoop bus through all the other caches, checking do you have this data already? Then if the data is already there and then it is unmodified, it will be brought to this cache. But if it is in an invalid state, then it will be cleared and then fresh data will be taken from memory. And if it is shared, it will be marked as shared. We have to be careful because the other core is also looking into the same data, so on. So it creates this complexity which hardware manages using this messy protocol. Now, there are other issues as well, which are explained in the SDM, atomic operations, right? So, which means that, so this means that there are locked atomic operations where um, uh, when this instruction is executed, nothing else should execute. Only this should run. So this we have to send a signal to other cores to stop it from proceeding, run this, and then proceed forward. And there are so many optimizations possible in this. And memory ordering is a very important problem because all the cores should have a uniform view of the memory. Like if one processor is executing and changing the memory, it should be uniformly visible to everybody. The same view should be available, right? And also serializing instructions because there could be dependencies between instructions. Now, talking about dependencies, let's say you write a code with 10 assembly language instructions. Now, you will think that CPU will execute in that order. Actually, it is not so, because when the decoder breaks an instruction into multiple micro ops, it put in a pipeline, and if one of the instruction is blocking and the remaining instructions are not really dependent on this, it can put that in the queue and actually proceed with the next instructions and come back to this, right? So this the out of order execution and speculative execution. So this is how a lot of optimization is done in the hardware so that the program runs faster. I mean, there is also branch prediction algorithm, which, let's say if you have a code with if condition, if x equal to something, you execute something, and then if it is not, you go through something else. Now the CPU will look at it, and then it has to fetch the code. It has to decide which code should I fetch in the first if condition or in the else block, which should I take. So it will apply very complex branch prediction algorithm, and it will think, okay, program is likely to take the first block, and I will prefetch it and decode it. Most likely it will get it right, like 97%, but sometimes it gets wrong. When it gets it wrong, you have to flush the whole whatever you prefetch, throw it away, and and fetch the remaining next block. So these are the places where the CPU designers will optimize, right? And also the other point which I want to talk about is the registers. Let's say EAX, EBX. Now, if you look at the hardware, there are no real registers like that, right? These are all again virtual abstract concepts. Hardware will have hundreds of other registers where it will say, okay, EAX will be put into this register one, and so on. So it will have this internal mapping, and it has its own register reordering and management process, right? So each microarchitecture will improve on this kind of techniques so that the program runs faster. Now I have this final slide, which I will end maybe in a couple of minutes. Talking about this multiprocessor, I give an overview of the complexities of multiple cores, right? A single processor with 4 cores. What are the complexities involved? Now, you take multiple processor. That means there are 4 different processors, each with different, like 4 cores each, and actually it complicates even higher, right? So we can think of this in 2 ways: UMA or NUMA. Uniform memory access is what it used to be maybe 10 years ago or so, where we keep adding new processors, but they're all sharing the same bus to reach the memory. This used to work, but very inefficient because CPUs are very high speed. They work in gigahertz speed. Memory controller is in megahertz, right? So a lot of CPUs will wait for data, and this bus will always be choked. So we go for this NUMA architecture where we put different pieces of memory and assign to each CPU. So the CPU can uh, access the memory directly. Now let's say a memory is stored here, the data is here, and this CPU requests or wants that particular data. So this CPU has to send a message to this CPU to fetch the data and send back to this through this interconnect, right? So it complicates a little bit, but then it's actually much faster because at the same time you can access 4 different memory areas. So this table shows a comparison of this UMA and NUMA, and nowadays all are NUMA architectures. Obviously bandwidth is high and so on. And this last picture, I will show one of the examples of Sandy Bridge architecture, how with 4 CPUs, each with having multiple cores, we can achieve this NUMA, right? So what I talked about cache coherency. You see how many cores are there. I mean, I sometimes use a system which has 192 cores, right? And like 64 gigabytes of memory. And imagine synchronizing across all the caches of all these cores through this interconnect, right? So cache design is very complex here, and also um, even multiprocessor, writing multiprocessor code, we want the interrupt routing to happen to the specific core where the handler is. So, I mean, it actually complicates the whole design, but there's no other option because when we want more and more performance, we have to go for this complex architectures like this. So I think I ran out of time, so I'll wrap up with this. I believe I have covered some of the next level of details of the ISA assembly language and the multi-core from what you have learned, and maybe created some curiosity in some of you to explore further and look at the problems. And there are always problems in all these things which will maybe influence you to look into this area and solve it in the future, right? So with that, I say I'm done. Thank you for this opportunity, and let's go for the next. I don't know if there is questions or.
Nish? Okay. Sir, I have a doubt. Like, if we create a language, like just like C language, which and that language is pretty much fast than the C language which we are using right now, so that we definitely need an assembler for that, right? Basically, the assemblers which we have are actually assembling the C code, right? So if in case we create such language, will Intel allow us to use such assemblers because it will not ensure the compatibility with the processors which are created way before like 8086, and the new assembler, if it doesn't provide the capability like the capability with the sorry, not capability, compatibility with processors which were created way before, will Intel support this kind of system, sir?
I don't really think I understood, because if you look at instructions, right, when you have design a new language, at the end of it, you have to convert it to some, you have to convert to some assembly form and then build the binary, right, into opcodes. And Intel ensures that opcode is always compatible with the previous ones. So now the only case which I can see is that you are using a new instructions which are not available in the old processors. Obviously, that will create a fault when we run on old processor, right? So, I mean, from Intel point of view, I don't think there is any restriction on developing a new approach, right? So,
Yes, sir. Of
yeah.
course, like if it is compatible with the processors which are being used today, which were created before 10 years of stuff, but when it comes to 8086, it is created way before, right?
Yes. So
So
there, the limiting factor is it has to be 16-bit, right? Any code that you write now are usually 64-bit or 32-bit, which will right away will not work on that old ones, right?
yes, sir.
Unless you compile it for 16-bit mode.
Okay. Okay then. If it is just compatible up to 32-bit, and if it is not compatible with 16-bit and uh, before that, so will Intel not support this kind of development?
It will obviously. I don't see any issue with that. Yeah, I don't think so. I mean, each processor has its own built-in error checking. So if there is an instruction which doesn't understand, it will create a SIG illegal instruction exception, and then the program stops, right? So that's a way to say that this is not supported there. So then we have to redesign the compiler to create instructions which are compatible to that particular processor.
Okay, sir. Yeah. Thank you, sir.